Well, good afternoon to everybody in the Eastern time zone or earlier than that. Good morning to the rest of you. Thanks for joining us again for one of these data-driven agriculture webinars today. It's 12:30, so we don't want to penalize you for being on time. We'll go ahead and at least get started with the introductory matter. I'm Dennis Buckmaster, a professor of Ag and Biological Engineering here at Purdue. I also serve as a Dean's Fellow for Digital Agriculture to coordinate things like this and assorted other, sometimes administrative work. I find that sometimes I take the whole day and actually don't do anything, but I coordinate several things. So, but we're glad that you're here today. We can go to the next slide. So this is a weekly series sponsored by, of course, Purdue Agriculture. You can tell that from the color scheme here and the logo there. We do have a Digital Ag Resources website. Probably those of you that have been here week after week, you know that. And we'll put the links to these things in chat here shortly. But on that site, we promote this webinar, other resources. We have a directory. We have a documentation of what the educational programming related to data science and digital agriculture is here at Purdue, both formal, undergraduate, graduate, as well as informal and extension opportunities. There is specifically a UAV site regarding uses in agriculture, and then much of the work that we do here is, at least for the time, sponsored by the WIN, the Wabash Heartland Innovation Network. Next slide. And it's great to see someone from Kenya. This is really nice. So you'll see the upcoming topics here in the next few weeks. We just have 5 more left after today. We hope that some of these would also be of interest to you related to more intelligent, smarter treatment of livestock diseases, a little bit more about uses of UAVs and sensors, using public data and those sorts of things. So we welcome you back each week. If you happen to miss one week, of course, they are all archived on YouTube in a playlist under the Purdue College of Ag, and we will get, since you registered for this series, we'll get those links to you in time. Next slide. So for today's webinar, as with the others, we greatly encourage you to use chat. Go ahead and just pose questions whenever they come to mind. Maybe if it's specific to a particular slide, maybe you want to mention something about that slide so that we can find it quickly in the end. So we would encourage you to sort of remain muted with your camera off during the presentation itself, but then at the end, we can, as long as the group is reasonably small, and it usually is less than 100, we'll let you unmute and pose questions, as well as pose them through chat. And I might do the same, posing questions through chat. So Varun, if you'd go ahead and start sharing your slide. Today, our presenters are Dr. Dharmendra Saraswat, a colleague and friend of mine from Agricultural and Biological Engineering. He is a UAV and a Geographic Information Systems guru. He teaches courses on this topic and, of course, does research in this area. And actually, I think the work that they're presenting today was just very recently published in the refereed literature. Varun Aggarwal is one of his graduate students doing this work. And so actually this is a shared presentation between the two. I believe Dharmendra will kick it off, sort of give us some context of where we're going. Varun will sort of explain how does this work? How can you identify weeds? And what is the technology behind this? And then Dharmendra will wrap it up. So without further ado, thank you very much, Professor Saraswat and Mr. Aggarwal. We appreciate your presentation today. We're looking forward to learning about weed identification.
Thanks, Dr. Buckmaster, for a very nice introduction, and welcome everybody. And I'm very excited to present this work on discussing the applicability of deep learning for weed identification using UAV imagery. And Varun Aggarwal, who is my graduate research assistant and ready to graduate by the end of this summer, is joining me for this presentation. And let us take you forward to this journey. So Varun, please go to the next slide. So let me give you a brief outline that after providing you background, some objectives and goals for this work. I will briefly discuss image processing versus deep learning type of questions that I have faced even from my colleagues. And then from the task 3 onwards, Varun will walk you through the results from publicly available data sets and why we created a new data set for this particular study. And then some preliminary results will be presented by Varun. And towards the end, I will provide you some further reference and acknowledgement. So next, please. So yeah, let's move forward. Uh, Studies have shown that if fields are not checked for weeds, the potential yield losses in Midwestern US would be close to about 50% in corn and 52% in soybean. And in terms of dollar values, this would be close to $42 billion every year. And just to give you an idea about this amount, that if you are going to save $10,000 every year, it would take about 11,500 years before you would be able to save $42 billion. And let me put my maths correct. You will still be short of $25 million, even when you save at the rate of $10,000 per year for 11,500 years. So that's the extent of the losses that farmers have to bear. Next, please. And the weed scientists, they recognize that the revolutions in computing power and automation have led to an emerging industry that uses machine vision and global positioning system information to distinguish weeds from crops and does enable delivering precision weed control. And there are a number of machine vision based commercially available solutions. A few of them are listed on the slide here, but you can also very well see that these solutions rely on ground-based identification with imaging sensors mounted on either a tractor or an autonomous moving vehicle, especially designed for weed control applications. And none of them identify weeds from aerial images. So that's where we are coming at. Next, please. So through this research, we aim to evaluate the performance of deep learning networks for applications in weed control. Because you can very well imagine that when we are talking about an aerial platform, that platform is going to be moving at a much faster speed than the ground-based vehicles. So we are interested in identifying those algorithms that can match the speed at which the UAV is flying, and at the same time allow us to distinguish between the type of weed and the crop, the location at which it is present, and also in some cases allow us to count either weeds or crop in the field. Next, please. And the overall goal of this research is basically to assist human scouts in identifying weeds by maintaining high accuracy and through the process of automation. So image processing versus deep learning is a question that has been asked to me even by some of my colleagues, that why you are not relying on image processing and what is the need for deep learning? So I have a good answer by now because, conventionally, the RGB images that we also known as the color images were used for detecting crops and weeds using some traditional image processing algorithms. And this approach has existed since 1980s, unlike deep learning that has come around starting 2010. And image processing basically relied on techniques such as thresholding and segmentation, but the thresholding process also required manually tweaking the threshold depending on the field conditions. And you can very well understand that this process is not subject to the kind of dynamism that we see in the field, because the moment illumination changes, a soil type changes, the crops and weeds changes, the surface contour changes, there is a need to find out a different threshold. Next, please. But as the science kept on progressing, new classification techniques powered by machine learning algorithms were also being explored for weed identification. And techniques such as the support vector machine, SVM classifier, and random forest, they started showing some promising accuracies. And though classifiers were very good at forming decision boundaries, but they were only good if the right image features were provided. Next, please. And when I say image features, then I am basically referring to higher order statistics such as kurtosis, edges, contours, corners, histograms, color thresholds, etc., etc. So while classifiers were better at weed identification compared to old thresholding techniques, they had an important precursor which limited their application. And this was choosing features which would lead to highest accuracy. And what this means is that for every application, a thorough search or features had to be found, and features which worked for certain field in, say, northern Indiana could prove to be useless for another field in southern Indiana. Next, please. So in a sense, I am at a position to say what are the limitations of image processing. So the limitations are that one has to find features manually. And secondly, the same features cannot be transferred to another field. So that means the limitations with feature transfer. Then the images that are acquired have to go through some pre-processing. And finally, because image processing relied on vegetative indices, and one of the most common one is NDVI, or normalized difference vegetation index. So it need to be calibrated from field to field. Whereas when I'm talking about deep learning, it enables us several advantages. Number one, the feature selection is all automated. Then transfer learning is also possible. There is very little image pre-processing required, and there is no need of vegetative index. So to take you forward with how this has been applied on publicly available dataset and customized datasets, I will invite Varun Aggarwal, my graduate research assistant. So Varun, please take it forward.
Hi, everyone. So essentially, given these advantages for deep learning, we wanted to test out how well it performs for the task of image segmentation. And to go about it, we first tested these models for public data sets. And then we recognized some issues with the public data sets. And then based on those issues, we kind of created a custom data set and then tested the model's accuracy on those. Now, this particular public data set comes from Brazil, and it is for a sugarcane field. So a UAV was flown at a variable height from 125 to 200 meters. And in the end, they stitched all those images together into a single big image of the field. And they were able to obtain a ground sampling distance of 0.5 centimeter per pixel. Once this was done, they also, and a human expert kind of annotated each of the pixels of this field into a class. So for example, they annotated the sugarcane with the green color, where each of the pixels where sugarcane was present was marked green. The weeds were marked with a yellow, and anything else like the soil in the background is marked with red. Given this, we started training the network, and the model we chose was DeepLab V3+. Now, what this slide show essentially is how well the network is performing as the training progresses. So epochs, when I say epoch, one epoch is essentially when you train your network on the images of the field from a single day. Now, what has to happen is you have to give the same field image multiple times for the network to learn so that it can learn better. It's almost like me trying to learn how to fly a UAV. The more I practice, the better I get at it. Similarly, the more I train the network with the same set of images, the better it's going to get. And that's visible from these results we obtained. So if on the left, we have the ground truth, and on the right, we have the predicted values. Now, if you see, in the first epoch, the prediction is not really very good. But as we are reaching 168th epoch, the prediction is very close to the ground truth. And these images kind of show how the how the prediction was after the training was complete for different regions of the field. So like for this first region, you would see that it's even able to identify the small little wheat patches which are marked with yellow and with the ground truth. And in fact, it's able to identify the big wheat patch as well, very well. But it has some, it was kind of limited in some other regions where you'll see in these blue circles, the prediction is not very close to the ground truth. Now, to quantify how well these two, the prediction and the ground truth kind of overlap, we have a metric called IOU score, which I will kind of explain later on how it exactly works. But for now, we got in score for this publicly available data set, we got 74.4%. And so essentially we're targeting a score higher than 50%, and anything between 50 and 70% is considered a good score. And anything higher than 70 is like an added bonus. So here, since the results was above 70%, we were very happy with it. And then we wanted to test it out more for our data set. Now, with this particular data set, we had some issues. Number one was that the images had a very uniform background. So it had only soil type for one variety, and since it's a single field, there was not a lot of variability. At the same time, this data was not temporal. And what I mean by that is, how at different crop stages, it is possible that the network has a different accuracy or the IOU score. At the same time, this data set was collected in Brazil, where the conditions are not not the same as in Midwest US. And therefore, we needed a data set, particularly for Midwest, so we can apply our networks for Midwestern region. So given this, we collected a data set of various images of various fields in Indiana, and we particularly collected images from early season weed. So multiple studies have shown that when the weeds are kind of stopped before they are over 4 inches of height, their impact on the overall yield is very minimal. And kind of that is why we are, we're trying to see the deep learning performance, because we want to increase the overall yield of a field. So these images were collected at multiple fields around Indiana, and in total we had 3 different fields with different soil types and different crops. So 2 of the fields are really close to the Purdue's main campus. One is TPAC and the other one is MEGS, while the third one is Winnemac. Winnemac and MEGS was a field for soybean, and the TPAC was a field for corn. And in addition, each of the fields had a different target weed. So for Winnemac, it was farmer amaranth. For MEGS, it was horseweed and water hemp. And for TPAC, it was giant ragweed. In total, we collected around 38,000 images over a period of 25 days from the early season. And for this data collection, we used 2 different UAVs. One was Mavic Pro and another was DJI's M600. Each of these UAVs was flown at a different height. So Mavic was flown at 5 meters, which gave us a ground sampling distance of 0.17 centimeter per pixel. And M600 was flown at 10 meters and gave us a ground sampling distance of 0.3 centimeters. Yeah, because we wanted to stitch these images together as well in the post, we employed ground control points or GCPs. And the way we placed it around the fields was 4 at the corners and the 5th one in the center. And for each of the ground control points, we kind of collected the GPS location with the Trimble Ag GPS base station. So once I have kind of set a stage for what all we did, I will now show what type of data we collected and what results we obtained from it. Now, this is like the image from 5th June for a field Winnemac, and it has the crop soybean and primary weeds at palm amaranth. So this is, I think, around 2 weeks into since emergence, and you will see that it's really you can barely spot the weeds in this image. There's some around here, some around here. And the soybean is also very small. And now in the further slides, basically, I will show the image from about the same area of the field. And you'll see how the soybean is growing as well as the weeds are growing and how their density is also kind of becoming more evident from the aerial images. So a week after 5th around, we have these images from 11th June, where you'll definitely see a big difference between 5th and this. The soybean is much bigger and you can easily spot the weeds now. And this is from 12th June, a day after. 13th June. This is 14th June. And this is 15th June. So if I go back to 14th and come back to 15th, you will kind of see that for some reason these the whole weeds and the soybean kind of look a little smaller. And what the reason for that was, like, we intended to fly the UAV at 5 meters, but because of some technical challenges, it flew at a little higher altitude, which was not under our control. And because of that, the weeds and the soybean kind of look a little smaller. This is from 16th June, 17th June, and finally the 18th June, where the soybean is much bigger now and the weeds are also much bigger. So given the data for these states, we also wanted to kind of go out into the literature and identify what all networks are being currently used for image segmentation. And this timeline kind of shows different networks where the imposition of the flag kind of marks when the network was first conceived or published. And out of these networks, we kind of chose 2 networks for analysis. And those networks are UNet and DeepLab V3. The reason we chose UNet is essentially because it's the most popularly used network according to us. And we thought that will be like a good comparative benchmark with the other studies. And we chose DeepLab V3+ because it claims that it is very good at identifying small objects. And when we are dealing with the aerial images, the size of the weed and the crop, or what we call objects, will be very small. And we thought that DeepLab V3 might be a good alternative to image segmentation. Once these images are collected in summer, we went out and started annotating these images. Now, annotation is like a way of telling or training a network what each of the crops looks like. So you can think of it as like, teaching a kid the English alphabet. You have to tell how an A or a B or a C looks like before they can recognize it. Similarly, kind of tell the network, hey, here's anything which in blue is going to be soybean, anything in red is going to be palm amaranth, and anything in gray is going to be our background. And to do this annotation, while there are multiple softwares available, we went and chose Label Studio. And the reason we chose it, number one, it is open source, which is amazing. And secondly, it's very flexible and customizable, so we can kind of adapt it for different applications of annotations. Once these annotations were complete, we also kind of identified what evaluation matrices we want. And one of them which came out and we found very useful was IOU, which stands for intersection over union. It's basically a ratio of 2 different areas. Now, when our prediction of ground truth images from the public data set, it's kind of measuring how well both of them overlap. So if the area of intersection divided by the area of the union, that's kind of a metric. To give an example, consider this. Let's say we have an image of a plant and we have a ground truth which kind of completely surrounds it. Now we have a prediction which is 100% over, which has a 100% overlap with the ground truth. This would mean it has an IOU score of 1, or in percentage 100%. But let's say it is not exactly overlapping, it is kind of misplaced by some one block. This will have an IOU score of around 0.72 or 72%. And we are aiming again at an IOU score between 50 to 70%, and anything higher is an excellent performance. So given that, we got some results for number one, the unit, which will be our benchmark network. And what you'll see here is the IUU score for the soybean here with this graph, and the IUU score for palm ramrod with this graph. If you look at it, this was 5th June images, and the IUU score is around 20%, which is not really acceptable. And it is not until 13th of June that we see it crosses the threshold for IUU. But for soybean, we are already seeing a really high early on, because soybean is much bigger than wheat in the images from 5th June. In addition, another point we noticed was on 15th June right here, we saw a certain dip in the IUU for palmer amaranth. And the reason for this dip was that on 15th June, if you remember, the UAV was flying a little higher than 5 meters because of its object size was small. And in comparison, let me go back to UNet's result and immediately to DeepLab V3. You see the transition of how the IUU kind of increases overall, all the graph kind of shift up. And with DeepLab V3 Plus, starting from 11th June itself, we have crossed the threshold of 50%, which is very, very exciting to see. And if you notice carefully, even on 15th June, we don't see such a significant dip in the accuracy as we saw in the unit. And in addition, even for the soybean, the overall IUU score is much higher, almost touching 90%, which is very, very good. And for soybean, it touches around 70% around 18th June. But now, given these results, we kind of had few challenges during this. And the primary one being, the smaller the plant, the harder to detect. In addition, the annotation of this plant, it is very prone to error. And the way I explain it, this interesting example. So given that we had a ground sampling distance of 0.1 centimeter, and we're looking at a plant which in the early season is only about 2 by 1 centimeter big. So in terms of the pixel or the number of pixels it's going to occupy in the final image, it will be around 70 pixels, which is like 12 times 6, around 72 pixels. Out of a whole image has around 12 million pixels. So out of 12 million, spotting those 70 pixels is difficult. And we can kind of, we are prone to making those errors of annotating a pixel in the wrong class because there are only so many available. So that's where we found that annotation is error prone, and that is going to affect the accuracy of the network. In addition, the annotation is very time consuming because we have to not only just annotate these 12 million pixels from a single image, but the images for the whole day. And to give like an estimate on the time, we spent around 40 hours of time for annotating the images from a single day.
Yes. So I would like to welcome you to please check out this recent publication from our group, where we have shared results from some publicly available data sets, and also the data set that we acquired using the AgBot competition for weeds that are common in corn and soybean production systems in Midwest. And one of the challenges that we reported in this study is that identifying grassy weeds using the Fleur Duo Pro was a little bit of a challenge. So this year we have a better resolution sensor, and we hope to come up with a much higher accuracy compared to what we got in our previous try. And with this, we are almost close to the end of this presentation. And before I end, I would like to acknowledge the support that I received from my collaborators, Dr. Brian Young and his wife, Julie Young, and their graduate student, Brent Mansfield, for collecting the data. And for this research was possible because of funding available through WIN, through the grant number that is listed there, and also the USDA NIFA, the HASH project. So with that, thank you very much. And I am looking at the chat. We have been able to answer some of the questions, and I look forward to answering further questions since we have more time available.
Awesome. Thank you very much, Dharmendra and Varun. It is very interesting work. Maybe you can look in the chat there. I posed a couple, and if anyone who's attending today has a question they'd like to pose, we'd invite you to either type it into chat or go ahead and unmute. You can turn your webcam on and pose a question. We've got the guys right here handy to address whatever's on your mind. I'm thinking about stumping them if I send them some pictures from my garden, which has taken off tremendously with lots of different weeds. Maybe they could help me assess that. But anyway, we want to answer your questions.
Okay, so let me search the link for publicly available data sets that we included in that paper. So in the meantime, if Varun can address other questions, I will provide the link to publicly available data sets.
I can quickly share that.
Thank you for the presentation. And I have some question about training or label data set generation. Can you elaborate a little bit about how many labels you have generated and how many of them are used for training, validation, and tasks? Do you have those information?
Yes. So these so for each day of data, we obtained around 152 images from Mavic. And these images were then further broken down into smaller parts because the whole image cannot be used to train the network at once. And we had around 192 images per 192 tiles per image captured by Mavic. So that's like 192 times 150 total images which you use to train the network.
I'm sorry to interrupt, but are you talking about the result that you're showing in the screen, or the question that we're asking is about the data set you acquired?
Yeah, so in the data set we acquired, so if you look at this, let's say we assume the image is from 5th June, we got 152 images for this, and each of the images were further broken down into smaller tiles. And for per image, we had 192 tiles. So if I give you the number on this, it's 192 times 150, which is a little hard for me to calculate, but should be around 4,000 or 5,000, more than that, sorry. But and in total, we had 3 different classes: the weed, which is palm amaranth, the crop, which is soybean, and the background, which is the soil, and the other weeds which we were not identifying.
And how many of them were used for training, validation, and tests?
Okay, so out of those, 50% of those images were used for training, 25% were used for validation, and the rest of the 25 were used for testing.
And here we have a very, very different approach than what you find in the literature. In the literature, it is very common that researchers report either 70-30 distribution or 80-20 distribution for validation and testing. But we went with 50, 30, and 20 approach as one of the collaborators with us from the deep learning side feels that this would be a better way to find out about the data and also make generalizations.
Thank you.
Yeah.
Hi, Varun. This is Azad Chahal from Purdue Extension. And I have a question regarding, I want to know, what's the correlation between the predicted values with the actual values, or is it different for soybean and for the weeds?
So you mean the final score for each of them?
Yes.
So yes, so I'll come back to this graph right here. So the metric we were using was IAU, and the graph in the top graph is for soybean, and the blue colored or the dark colored graph is for farmland. And what you'll see is the IOU for the score for soybean is much higher than for weeds.
Okay. And you mentioned in June 14 and 15 is a significant drop of IOU score. What, like how you define that significance, like how you say that, like what was those number with that tells is a significant
Oh,
difference? Yes.
so yeah, so if again, I'll come back to this graph. This is like from 14th June and 15th June. So in general, what you were seeing is like a positive trend where the IOU was kind of increasing as the days are progressing because the size of both the crop and the weed is kind of increasing. But here on 15th June, we see a drop of around 8% between for the IOU score, and it almost like comes close to our minimum threshold 50%. So that was a little, on the edge.
Yeah. So my question was, let me rephrase a little bit. Like, what's your number? What's percentage considered as a significant drop and increase? Like it's like a 5. It's basically based on how much, how your percentage is representing your data, right? So what percentage is like you can say, okay, now is significant. So how you like your significance defines it?
I think I do not have an exact number on this, but I can get back to you about that exact significant number, like, how significant is a drop of 1% versus how significant is a drop of 8%. But but essentially what we want is that score to be higher than 50%.
Oh, cool. No, thank you. Thank you for a wonderful presentation and work. Thanks.
And then Varun, you may also share the link to the Brazilian data set that has been used. Yeah.
Let me quickly do that here.
Did you see Bruce's question there having to do, I gotta scroll back to find it here.
Yeah, I'm just going through that.
Good.
Yeah.
One more.
Yeah.
So one more quick question. So you collected data in 3 different locations with 2 different platforms, and I'm pretty sure, depending on the location and depending on the sensors, how well, this the model that you develop, generalized to another environment. So I'm not sure whether you had a chance to test that out to see, the model that is trained from one location, try to apply to another location to see how well it works. And another question that I have is that you also have collected data set over multiple times. In your training process, are you putting all those data collected from different dates as the trained data set as a whole, or are you trying to use a training data set that is fairly close to the season they're trying to apply to?
Okay, so I think I can address them. I think the first part of the second part, let me answer the second part of the question first, which was like, when we are training, we are only training for images from a single day, not for multiple days. So like if the images are collected on 5th June, the model is only trained from 5th June. And if you're training a model for 11th June, those images are only from 11th June. Right.
What about the data set from another location? You're only using the data set from one location and one day at a time?
We are only using data for a single location at a time. So single location, single day. That's how we are training.
Okay.
And to answer the first part about the generalization, that's an excellent idea, and that's something which we'll be exploring in the future, where like how well a network trained on a particular field generalizes for another field, and how well images, how well the data collected for one date generalizes to another date.
I mean, the reason why I'm asking is that in order for this application to be useful, like we cannot fly the UAVs on the same day that you collected a training data set on. So you should be able to generalize the good enough so that this can be useful. So I just want to comment on that.
Yeah, and this the upcoming production season, we have intention to really implement this on a UAV. and have a first-hand experience that how well the model that was trained on previous years data is going to work for this production season, and when the weeds and crops are at a comparable stage.
And I'm sorry, I'm kind of dominating and asking too many questions, but Dr.
No problem,
Saraswat, you mentioned that you guys are upgrading your sensors to the higher resolution. Do you already have one purchased? Because
Yes.
the reason why I'm asking is the DJI and the Mavic Pro, which is tiny sensors, and for your Duo Pro, this is also even smaller than 1 inch sensors. So sensor size is fairly small. So even though you're gonna get, I'm not sure what is a 12 megapixel images you're getting out of it, the image quality is gonna be so, so. I mean, I'm not going to say poor, but it's not going to be as good as from the one that is collected from much larger sensors.
Yeah, you are absolutely right, and we are not going to use Mavic Pro for this year. We have M600, and then we have acquired M300. So, and then we have built kind of camera attachments for these two UAVs. And that's what we intend to use. And then we have some newer Sony camera that provides us much higher level of resolution than what we had this for previous year.
And for your information, you probably have an M300. Gemius P1 just came out, which has 45 megapixel sensors with a full frame size. And the micro is using that one. And that one is, I'm so happy with that, and if you may want to consider that as an additional sensors, because at that the altitude is going to give you the very good quality data set to do exactly what you're doing right now.
Thank you. Yes, I mean we just acquired M300 a couple of months back, and we know that we will never be able to beat these companies in terms of creating better quality products. But then we also have resource limitation.
One more, I'm going to ask this question. I'm going to just be quiet.
Yeah.
So, Varun, you mentioned that you are installing GCPs around the field, and seems like you're doing a SFM processing to create the orthomosaic out of it. But in one of your slides, you mentioned that your overlap is only 20%. So I'm just kind of curious, are you doing SFM, full SFM, structure from motion, or are you just stitching images together?
So the images from Mavic Pro, those won't be stitched together, but the images from M600, they will be stitched orthomosaic. And the reason we are not stitching from Mavic Pro is because we wanted to fly it at a lower altitude in an automated flight plan. And when we are doing it at 5 meters, the only way to fly it at 5 meters in a flight plan was by reducing the overlap. So that was the reason.
Yeah, that was a limitation of the UAV. So, and then that's what, when we were looking for M300, we figured it out that we will be able to fly at a much lower altitude. Of course, it will not be a continuous flight. It would be stop and go, but still it would allow us to acquire very high resolution data, better than 0.17 centimeter pixel size. That should give us some good data set for processing for the upcoming production season.
So my question is, how are you going to reference those detection to specific location if you're not doing full SFM then?
So in this collection season, we have an RTK based M300, so that will definitely help us in doing the orthomosaic.
Probably, Varun, you and I can have a more technical discussion. I don't want to kind of overload with the too many other technical this question, but I have more questions to ask, but I want to let others to ask some questions as well.
No, we can always have conversation later on.
Yes, I would encourage you. I would also encourage you, Jinha, because Varun's going to graduate soon, you're going to want to attend his defense.
Okay.
So maybe you extend an invitation there. I do want to come back to Bruce's question. I think it's a valid one because this is such big data. There is a lot to process. And so how is it scaled up, in a practical sense? Any thoughts with regard to that? You may have to look at Bruce's wording, but I'm just kind of using scale up as a simple way of addressing that.
Yeah.
Yes, and this is how I am looking at it, is that once we have trained model and we have implemented it on the UAV, then we would like to see that it replicates the way it has been trained to identify weeds. And if it is able to do that, then probably that is going to be an answer as to how we are going to handle that data set. I wish that I can tell you definitely at this point of time that large data set has no meaning to us, but no, I look at it as a large data set and a problem that needs to be solved.
Okay. Any other questions from the group? Maybe I'll just have Randy share the upcoming webinar slide just while we still continue some Q&A. One question that I had posed there, I'm really curious about, that's why I posed it, is can you train based on a purified image set, like only show the training, this is this kind of weed, this is that kind of weed, this is a soybean, this is corn, but then apply that learning in the real situation where they're not in monoculture? Can you do that, or does it require that the training come from real images?
So can you kind of repeat the end of your question a little bit? Like, where do we want to apply this?
Sure. No. So I'm saying, let's say, well, what was the, so you were dealing with Palmer amaranth and soybean, for example.
Yeah.
Maybe I could just have a field that was solely Palmer amaranth, and I'm just training it. When you see that, that is that weed. Then you have another field that's pure soybeans, no weeds at all. And you train it so that when you see that, you know it's a soybean. Now, can you use that learning in a situation where there might be amaranth amidst soybeans?
Yes. While we haven't done experiments on this, but let's say we have a network which is good at identifying soybean, and then it goes to a field which has some noise or basically other plants in addition to soybean, it will be able to single out the soybeans out of it. I think it will be able to do it.
Okay, good. So a couple new questions there in chat. Maybe you could address those.
So I think I'll start with Daniel.
I am responding to Daniel. So yeah, Daniel, I can say that this technology is not crop specific, and of course the efficacy or the accuracy of identifying weeds could vary based on whether we are looking at the broadleaf weeds or grassy type weeds. But I think crop will not pose a major limitation as far as my feeling goes. Varun, you are free to add any other points that you would like to.
Yeah, I mean, definitely. As you also pointed out, with transfer learning, as we are kind of, reapplying these networks for other applications, we will have to train them again from scratch to kind of identify tobacco, cotton, and hay or pasture, basically. So we will have to retrain them, but then the training time and the training efforts will be much less because of this transfer learning concepts in deep learning.
Yeah, and then Savan, your question is about actually removing them. We are not looking at the weed removal, rather weed management could be the solution that we try to answer long term, and that would mean that that we come up with an ideal combination of the deep learning algorithm that works pretty fast, and also the actuator that works in sync with it, so that the 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 UAV can treat the spot at which the weeds are present rather than 10 meters or 5 meters away from it, just because it is flying and the actuator is not able to match up with the analysis speed. So that part we have not done, and some of the published research also indicates that there is some time lag that exists at this point of time. So this is a question that we are also interested in finding an appropriate solution in due course.
Yeah, can I just say one thing? This is actually a question that I was just attending one of my alumni association meet recently, and there is a particular entrepreneur who is working on developing stevia-based solution. So she proposed this question to, like, a lot of computer scientists and engineers that, we need some form of technology where a lot of computer scientists are coming up with like startups which are related to computer science technology. But is there something that you can develop so that weed removal can be done? So that's the sort of having like, seen your presentation, I thought maybe I will pause the question if there is anything, but that was the sort of origin of the question. But thank you for your answers, and look forward to it, and great presentation. Thank you.
Yes, Savan, the challenge is that weeds are also present in the middle of the crop. So when we are looking at weed removal, even the mechanical means that are available, they are not that very efficient to really take out weeds that are present in between the plants. So they are very effective to remove weeds that are present between the crop rows. But when the weeds are in the middle of the crop, then you do not want to disturb the crop. So that becomes a challenge.
Right. Okay. Yeah. Makes sense. Yeah, that could be a clear problem. Yeah. Thank you.
I think we have them mostly addressed. Any closing remarks, Varun or Dharmendra?
Yeah, we are very, very, very thankful to you for inviting us, and a great participation. I was very happy to see 50 plus at one point of time. That is now down to 29. Is still very respectable as far as the seminar presentation goes, and great questions. And Jinha, I would like to have this conversation going. Great questions, and we would like to prick your brain to really keep moving forward in this research.
Great. Well, I wish you all a great spring day, spring week. Hopefully we'll see most of you come back next week. Thanks again, Dharmendra and Varun, and all of you who are participating today. Thanks so much for attending, and we'll see you next time.
Sure. Thank you.
Thank you,
Bye-bye.
everyone.